Language is an interconnected web of meaning where words are the nodes and relationships form the connections between them. If you pluck a word, the words around it vibrate, change the context, and it alters its pattern of vibration. As humans, it's easy for us to grasp how changes in context alters the meaning of words. But to a computer, words are just a sequence of numbers. Intuitively, we know that light has 3 different meanings here, but the computer is going to represent light the same way regardless of context, which to us doesn't really feel right. This causes the words to lose their inherent meaning, and the web of language falls apart. What we need is a way to teach computers how to understand language more like a human so that they can build their own web that works just like ours. What we need are word embeddings. Word embeddings are a way of representing text as numbers so that computers can understand the relationships between words, capturing their similarities and differences. Word embeddings, also known as word vectors, come in all different shapes and sizes, each with its own creation story, characteristics, and real-world applications. And the embeddings you'll be introduced to today are called TF-IDF. TF-IDF, or Term Frequency Inverse Document Frequency, is an embedding method that tells us how important a word is to a document within a collection of documents. This method considers all documents in the collection, so the size of this vector is equal to the total amount of unique words in the entire collection. Let's look at a popular application of TF-IDF known as topic modeling. Topic modeling aims to answer the question, given some collection of documents, tell me what each one is about. It starts by counting how many times each word appears in the document, then dividing that number by the words in said document, which gives us our term frequency representing how often a word appears in the text. But in bigger bodies of text, words like the, is, of, and so on tend to appear in abundance, while also carrying very little meaning. This is a problem for our topic model, since these aren't the types of words we want to use to describe an entire document. We need a way to reduce the impact of common words while adding emphasis on words that are more rare. So not only do we want to count how often a word appears in this document, but also how many other documents contain this word. This is our IDF score, which tells us how rare or common a word is in the whole collection of documents. Lower scores indicate common words, and higher scores point to words that are more rare. Multiplying our original term frequency with each word's inverse document frequency gives us our final TF-IDF score, where higher scores means greater importance. A TF-IDF vector represents the importance of each unique word across a collection of documents. So 10 documents, each containing 100 unique words, leaves us with a TF-IDF vector 1,000 numbers long. Once we've constructed a TF-IDF vector, we'll also know for any given word which documents are most relevant. This makes visualizing these vectors much easier since we only need to show 10 numbers rather than 1,000. In this case, I've topic modeled 16 podcast episodes and used TF-IDF to extract the top 5 most important words as topics. In this first episode, a conversation with Adam Rutherford on humans, animals, and life in general, the topics are Homo, species, population, year, and chromosome. If we visualize the word embeddings as a heat map, we can see which documents light up for each word. Other than year being relevant in almost all other podcasts, only the original podcast contains these 5 topic words. If we look at a different podcast like this one on gravity, we can see a whole new group of podcasts light up. Notice how words that are relevant in this podcast are also relevant in a few others, indicating that all these podcasts are talking about similar concepts. With this information, I could recommend new podcast episodes just based on the episodes with similar topics. And the applications don't stop at topic modeling and recommendations. TF-IDF can also be used to rank searches in search engines, spam detection, and more. While TF-IDF is undoubtedly useful, that's not to say it doesn't have any limitations. TF-IDF lacks semantic understanding. For example, bank and bank account and riverbank are seen as identical even though we know that they're quite different. Similarly, TF-IDF struggles with synonyms. Big and large might mean the same thing to us, but to TF-IDF, they're as different as apples and oranges. This can lead to misconnections between similar concepts. And lastly, TF-IDF completely ignores word order. So dog bites man and man bites dog look the exact same to it. Although very useful, these limitations highlight why TF-IDF isn't always enough for complex language tasks. To truly capture the complexity of human language, like the semantics, synonyms, and the importance of word order, we need to step up our game a bit. But that's a story for another day.